Good afternoon, everyone. Just as a quick start, I just want to start off with the fact that we acknowledge the traditional custodians of the land we are meeting on, the Ngunnawal people. We acknowledge and pay our respects to their continuing culture and the contribution they make to the life of this city and this region. We also acknowledge and welcome other Aboriginal and Torres Strait Islander people who are present today. So to kick it off, just as a quick introduction, my name is Dan Carpata. I am the go-to-market specialist manager for databases for our public sector organization worldwide. A little bit about me, started on my first, I guess you could say probably Oracle database back in the mid-90s, if you don't consider FoxPro and Access before that. So I've worked for Sybase, Oracle, I've been doing databases on and off for the last 25 or so years. So a little bit of background on me. Going forward, just want to talk today about sort of the history of databases, some of the key attributes of modern database applications, the architecture that we're looking at, modernization at Amazon, and then trail into the pursuit of what the ideal database is and how we can get you to modernize your database and your data platform. So the whole idea today is, right, if you're aware of AWS at all, I don't want to go into just a pure straight discussion of AWS databases, but I want to make it sort of thought-provoking. So I start off with this image up here, and I'm, especially for these type of sessions, I'm more of an answer and response person, but can anybody try and think of what I'm trying to portray up here with this image? And you can just shout it out. But we've got an old typewriter, and in essence, the point I'm bringing out is actually the keyboard. If you look at this, this is a standard QWERTY keyboard we all develop with and type on today. And in reality, it's not, and this is arguably so, not the most optimal keyboard out there. It was actually built because back at the time where you had these key strikers, that if you hit multiple keys that were next to each other fast enough, they would actually lock up and you would actually freeze and you have to pull it down. So how many people played with this when they were a kid and just hit all the keys and they would lock up and you'd pull them down, right? We all remember that. But that's the exact point. And most of that's mainly true, but the question is, why is it still the optimal keyboard today? And right, that's economies of scale. You're not gonna go retrain everyone how to type. And that thought process sort of goes into everything else that you look at, right? You can look at how companies have stagnated. You can look at how Blockbuster and other organizations that were brick and mortar have not been able to move into the internet era. But when you think about devices, the question is, why are you still doing what you were doing yesterday? And is it the right thing to do? So that's sort of what I want to sort of really kick this whole presentation off with. So if we take a look at the evolution of databases, and we're just going to fly through this, right? When Edgar Frank Codd came out with the relational data model, we've got sort of these three main databases. And I actually struggle with this because I have Oracle, DB2, and SQL Server. So as I mentioned, I actually worked for Sybase for a while. And so I take exception that we don't list Sybase in here, but SQL Server and Sybase, were sort of cohorts in creating SQL Server. And those lasted for quite a long time. Right? Then you got some more open source databases, MySQL, Postgres. And then in the mid-2000s, you have the plethora of databases that then emerged. Right? You can go through all of these, and you can see one key feature, especially everything was going around, the internet era is starting, as well as AWS started form in 2006. And that's where we started bringing out more services. And you can see as some of these databases expand, that's going to roll into our presentation a little bit. As of today, there's 340 plus databases. If you ever go to DB Engines, always look at that, and that tracks sort of which database engines are being the most popular, which ones are being leveraged, and they're good data points to look at today. So I'm going to go into a little history. Anybody say that, let's say, Oracle might be the first database? I mean, how many years ago do you think the first database was actually created? And if anybody's read the same content I've read, I go all the way back to the first time anybody started tracking data. I even go further back, and I was trying to find some material where I could say truly that there were cavemen counting the number of sheep or herd that they have out there. But what it comes down to the fact is once you got to a point where you can't remember everything you need to know, like which bush is poisonous, which snakes are bad, which ones are good. You've got to keep track of that somewhere. So around 5,000 years ago, the Mesopotamians started with clay tablets. And then I even take into the fact they added calculations, signatures, and seals, right? They were pretty innovative at the time, right? You think of signatures and seals. It's a whole lot easier to capture that than it is sort of your two-factor codes today. But if you could verify a signature or seal, you at least were trying to stamp it. And then now the medium is starting to change. You've got papyrus, you've got bamboo, you've got silk and paper. So now you can start keeping track of more data. It's a little more durable, right? If you ever want to sit there and talk with a friend and think about, how bad it is if you lost a database or something and you had to recover. Just think about when they dropped a tablet or something caught on fire. There was no real good backup or recovery back then. So that's always good for sitting around and thinking about that. And then you start getting into more data being created, right? I track back 700 years ago, they talk about the Italian merchants keeping track of their double entry accounting systems, credits, debits. Now you're keeping more data volume, having more paper. How do you store it? How do you volume this? And this is where innovations start growing from. So going back to the first database, IDS, the first integrated data store, which led IBM to create the IMS, which was a hierarchical database, wasn't very efficient for querying databases, right? So I mentioned that because you start talking about, we can store all the data, now how do we actually query it and get to it faster? And so the querying pattern is what we're gonna talk about when we talk about purpose-built databases. But then Frank Codd solved that problem with relational databases. And then I use Yahoo as an example of Hadoop, which once the data started to really explode, you started to run into areas of how do you now store this a lot cheaper? How can you store it and recover it faster? And then Hadoop came. And Hadoop is sort of the example of the typewriter that's come and gone, right? It's still there, but I like to sort of show, if you just take a look at like a Google Graph, how many people are actually looking at Hadoop? Or now that all of these data, these distributed file systems can now be stored in the cloud, they're really just cloud data. And so I sort of took this graph, and you can see the cloud data actually just mapping above what people's interest in Hadoop was. So I don't know if anybody else does that. I always sit there on Google Trends and pick up 2 terms and see how they go up and down with history. So it's pretty good in just tracking where people are at these days. So the computing paradigm has changed, right? And this has driven the database technologies that are out there. Back in the early history, disk and RAM were expensive, wasn't as fast. Storage and compute was put into one place. You had the whole client-server technology. You come to today, now we have widespread networking. It's cheap storage. You no longer need centralized databases. They're good, but you can actually spread this out. It doesn't have to be a single place where you actually query the data. Bandwidth is sort of 100 times greater. RAM is cheaper. Flash memory is there. And so taking all this into account, there was a new paradigm that had to be created. And AWS first created this new paradigm with the infrastructure with web services when they came out in 2006. So any data presentation has to have more data. So I love graphs. I love data. Data doesn't lie. I always say it's how you portray the data, whether it's true or false. You can skew it either way you want to. But 2 things to look at. One is commercial databases versus open source databases. And that's continually grown together over time. If most of us understand, most commercial databases were created because of redundancy. You needed something scalable, something redundant, something that was tolerant if you're going to put your business on it. And open source has slowly grown to actually close that gap. And if you look at the databases out there, I sort of have 2 graphs, and I actually show a little bit from 2013 to 2019, where originally the top 3 databases, Oracle, MySQL, and SQL Server, were well above any other platforms out there. But as you can see, it's grown. You get some now purpose-built databases, as I would like to call it, where you have Elasticsearch, you have Redis, you have Cassandra. But these are starting to grow over time because now customers can afford it. There's more platforms they can leverage it. And then just over the last few years, this has even changed. So even this has changed quite a bit. If you notice, the top 3 actually dropped down in their scale as the others have moved up. And I found it interesting when I first queried this that obviously Snowflake had made quite a bit of dent into the market when they came out with their data warehousing technology. But you'll see a lot of these jump up. You'll even see in the right side, you have a lot more databases that are more purpose-built that actually come up this line. I don't draw the lines because they're a lot. But it's showing you that the relational database dominance is dropping, and more of the purpose-built ones are growing up as well. So let's talk about the key attributes are for modern applications. We break these down into the 7 key attributes. And the first one is innovation and agility. Obviously, we're developing applications because there's a purpose. but we want to make it as agile as possible. So what are you innovating for? What are you building for? And as you build it, you don't want to stifle future innovation and agility. So you got to make it very agile to continue developing in. But you can't sacrifice performance and scalability for that. If you design something and you say, great, I can support 500 users, well, you want your business to grow over time, so you can't stifle performance. You got to make sure that your return and your response time stays the same no matter you go from 500 users to 5,000 users, and whether that's from today to tonight, back down to tomorrow. So you can't, the whole idea is making sure that you're not constraining yourself with the performance of your applications. And then last but not least, it has to be highly available, has to be easily managed and cost effective. No use in designing the greatest application in the world if it costs more than you're actually going to make in profit. So sometimes those are no-brainers, but I always like to bring those up at the end just to make sure we're not over-designing, because you can over-design. And the fact of the matter is, all of these applications can be built on relational databases. But is it the most effective use of the time? Is the most effective way to get that application through? So let's take a look at the modern data architecture. I'm going to take a few minutes here breaking down sort of what you see from the left side to the right side of the screen. So your traditional monolithic applications, traditional 3 tiers, your web tier, your application tier, your database tier. There's a couple problems in the past, and we'll go into this over the next few slides. In reality, that's a lot of the runtime coupling that you're doing with your application. So when you couple a lot of these applications together, it's a whole lot harder to break those out and get into more of a microservices sort of deployment. So anytime you need to make a change to one component of the application, you have to see how that's going to affect the rest of the system. So being able to break those out are key. So that's the runtime coupling. The biggest problem that follows after that, which is where I found here at Amazon, is the design time coupling, right? And if everybody's heard about how Amazon has grown from a monolithic application to where it is today, which we'll talk about, that design time coupling, it's great if you break this out into multiple runtime applications, but if you're designing all in the same team and you're not actually breaking those apart, you're going to get stifled by your design time as well. So breaking that out is key. So we'll talk about design time in a second, but if we talk about the runtime coupling on the right side here, with the microservices, you want to be able to decouple the architectures at all the different layers. So at the presentation layer, you want to be able to deliver a web, a cloud, API, different interfaces for users to come into. At the business logic layer, you got to be able to break that out, whether you have serverless technologies, using AWS Lambda. There's other technologies that you can use in terms of sharing messages around. You can use Fargate. A lot of these technologies allow you to break out that business logic, run it in different components of the application to break down that runtime coupling. And then getting from there to the data, which is where we're going to spend most of the day talking about, are different queues and caches and messages to get to that layer. So whether you're using SQS, whether you're using Kinesis or Kafka to order these messages, once you get from that layer, the question then is, how do you get to the data and what data are you getting to? And does it have to be the exact same database? The question is, does everything have to be in a relational database? Now that you've actually broken up the application layer, the presentation layer, into different microservices, these can all access different databases. You don't have to restrict yourself to one platform, where in the past, everyone was stuck with relational databases. So what I want to talk about for the rest of this presentation is mainly, how do you go about doing that? How do you decide which parts of the application do you break up? What is the best use at the data layer of this application? So going back to the design time coupling. Back in Amazon, we had this huge monolithic application we created back in 2001. With that database, it was directly affecting how fast we could make changes to the application, how quick we could get it to market, and not affect other pieces of the component. So a big thing that Amazon had was, how do we break these into smaller groups? And so the whole idea was agility so that we could enable innovation. And the big thing we wanted to do, and this is one of the key components, is we want to just increase the amount of ownership of each team, but decrease the scope of responsibility. So I want to make that very clear, because that is the key thing when we talk about our 2-pizza teams here at Amazon. So if you haven't heard about what a 2-pizza team is, the idea is that one person can really only effectively manage a 2-pizza team. So we can go into the pros and cons on whether Joe eats more pizza than Sarah, but in essence, about 6 to 8 people, 6 to 10 people, that you can manage a team that you have impact on one area of your focus of work. So whether you're focused on a presentation layer, whether you're focused on a database, whether you're focused on just the reporting aspect, breaking that out so that you can break this monolithic application into design teams that then create the specific interfaces with their services. Now there's tons of APIs, there's tons of messaging that goes around depending on how you develop this application, but this allows you to create that modular application. Microservices wasn't new at the time that we built this. The fact of the matter is it really takes not just the technology to do it, but also the thought process of the leadership in the organization to make this happen. So now let's get to the database, right? The whole idea is the history of databases proves that purpose-built databases is the way of the future. What is the ideal database? So if we break it down to some of those 7 features I talked about, innovation, agility, all storage patterns, you can make it ACID compliant as well as strong consistency, limitless scalability, that'd be great. You can just support any amount of load on there, and it's highly performant, and it never goes down. It's easy to use, it's cost effective, and it's predictable, right? So anybody want to pick the database that does all of that? It doesn't exist. And it doesn't exist, and I'm going to take a drink of water as I say this. Even though some people say it does exist, let's say multimodal databases are about as good as cutting down a tree with a Leatherman pocket knife, right? There's a whole reason that these tradespeople come to your house with tool belts. They don't come with one tool to actually fix everything in your house. They're not fixing the pipes. They're not, fixing the shingles with a Leatherman pocket tool. So I was going to make another joke, but we'll leave it out of that. I got lots of jokes. So that's the reason for the explosion of database solutions, right? We talked about the original 3, Oracle, SQL Server, but so many more has come out since then. You've got more purpose-built databases like MongoDB, Cassandra, HBase, and then you've got all the ones that Amazon has put out there and AWS has put out there to support these variety of applications. But what we found is that the query patterns are just a handful of them, right? We said there's 340 different database engines that DB Engines was tracking. And what we found is out of all those, there's lots of duplicates, and the query patterns really break down into a couple of these. So the ideal database is really broken down into a relational database. You've got key value, your DocumentDB, your wide columns, graph, time series, ledger database, and there's a few more out there, but that really helps you break down to what our thought process here at AWS in building out these database platforms. So the question is, where do you start? You've got your big monolithic application, your big database. Where do you go to from there? How do you get from A to B without feeling so encompassing? And I like, I've been doing a sort of talk track that I like to compare it to. You don't go out and climb a mountain. You don't climb Mount Everest, deciding the next day that you want to go work out. It leads up to that. It's a year, it's 2 years' time. You have to plan, you have to train, you have to buy all the right supplies. So it's not that simple. And what we've done to help with this is obviously we help you with that journey. And some of the things that we've created is our database modernization playbooks. So when we talk about the different playbooks, really there's 3 main plays that we see happening over and over again. There's the move to manage platform, there's the breaking free from legacy databases, and the modernization with purpose-built databases. So move to manage is really focused around going from a self-managed database on-premise to a move to managed database in AWS using, for example, our RDS platform. So taking Oracle on-premise and running Oracle in the cloud, right? The first step, as we'll go into the next slide, sometimes people start with just the lift and shift. Let's just run our compute and run our storage in the cloud. There's a lot more innovation and a lot more cost savings you can get if you just take that extra step of managing that platform. Then the next idea is, how do I just break free? How do I get to an open source platform? How do I break free from these commercial entanglements that I got from licensing and cost? And the idea is behind breaking free from those commercial applications to open source. And then you're left with the ability to innovate. As you start breaking down these applications and breaking down the use cases, you can start breaking down the purpose-built databases that you want to go from this monolithic to microservices environment, if that makes sense. And if you think about the path as you go, you will slowly create a lot more innovation and velocity as you reduce your costs, as you get more invested within the cloud. We start on the left. Lift and shift would be, as I said, just taking your infrastructure, putting it in the cloud, running it on EC2 and compute, just like you were doing on premise. Hopefully you can at least take advantage of some of the factors of being able to fine tune the application, because now you can easily swap in and swap out hardware to where you don't have to order servers in and out. So you get some benefits if you right-size the infrastructure. I can tell you I've seen customers that just thought, I'm going to lift it on-premise, put it in the cloud, I'm going to match the number of CPUs here and there, and they're like, I don't get it. It doesn't seem the same. It seems like I might be paying more. Well, that's the whole idea, is you provision for peak time during Christmas, and for 364 other days of the year, you really don't need it. So, make sure you tune for what you need. As you get to move to manage, you can start taking on the benefits of the managed platform, reduce a lot of that redundancies and handling the backups and recoveries and all the administration of the database, and focus on innovation. Then you start breaking free and saving some of the licensing costs, some of the costs that you have from the third-party vendors, and obviously you get to your modernized platform. So it's a journey, right? Let's dive deeper into what that journey looks like. So start with your existing application, right? The easiest thing is start where you're at. You're not going to reinvent your business overnight. If you are, that's great. We can go talking straight into building applications using AWS services. But take a look at existing applications. They're typically monolithic. They're made to fit and shoved into a relational database. But also if you do have new applications, if you have a lot of object relationship mapping or document mapping that you want to get straight into the environment, we can take you straight there as well. So it's good in both sides of the journey. So move to manage is always our first step. We've got 4 steps we're going to go through today. Take your relational database application, take it to a managed platform. You get the ability of taking all of the resources I mentioned on the last slide, reducing your operational burden, take advantage of the platform features that you have, backup and recovery, the capabilities to do quick failovers, quick failbacks. Just think about the time, if anybody in here is a DBA or has a team, how much time you go through testing, failing over, failing back. A lot of just that operational burden that you have, that becomes a lot easier when you have a managed database platform. And usually our relational databases, we're starting with RDS and Amazon Aurora. And what our RDS platform is, it's our relational database. We say there's 6 databases out there. We support the open source databases like MariaDB, MySQL, Postgres, the commercial databases of Oracle and SQL Server, and then also the Amazon Aurora relational database as well, which is built on top of a Postgres or MySQL platform. So they're easy to administer, allows you to easily deploy and maintain your hardware, performance and scalability. Now you can scale your compute and storage with a few clicks with minimal downtime. The availability and durability. We have the capabilities to have what we call our multi-availability zone, data replication, automated backups and snapshots, as well as providing a secure and compliant environment. There's no use in going to something in the cloud if it's not going to be secure and not be compliant as well. And let's dig into Amazon Aurora a little bit. So as you start going into innovation, the key idea is being able to take these open source databases and make them really a commercially stable database. So why I say that is, customers always wanted us to deliver a open source database that had all the commercial grade features, like the backup and recovery capabilities, some of the automatic failovers, the ability to backtrack, go back in time at any point in time in the database. And that's what Aurora provides you, but with added performance as well. So one of the things that we did is we actually separated the compute and storage. Allows us to have a high throughput and availability of the databases. A lot of the times when you take a look at separating compute and storage, you get added performance benefit for your application in real time. So think about it. You're not running backups on your production server every day now. All that's being done at the storage level. So a lot of stuff that was done on the compute is now on the storage. So when people think about going from even going from, say, a Postgres to an Aurora Postgres, there's going to be added capabilities and added performance features that you get because you're actually offloading the storage onto a separate layer. It also allows us to provide global databases, 6 copies of the storage across 3 availability zones. You get the pay-as-you-go pricing, the global database. And just recently, we now have our serverless version 2 database clusters that are instantly scalable. So now we're actually taking the database, providing it serverless, so it can help you as you grow and shrink with little impact to the application. And so I like to draw this evolution of relational databases. This sort of screen here is something I built to sort of try and draw the relationship of what this looked like over time. And this wasn't 1 year, 2 years. This was over about the past 10 years. When you take a look at originally just putting all your database software on EC2, going to Amazon RDS, which was created to allow you to help offload all of that administrative features. You now see with Aurora, we've separated storage and compute. And now with our serverless fleet, which is actually going into a lot of our other database applications as well, not just Aurora, but if you look at Redshift and other data services, we're actually creating that serverless fleet to where you handle not just the storage that's separated, the compute, but even the router, handling the connection so that from the end user, they don't see a difference on where they're going to and how they're accessing the data. A good example is PowerSchool. We'll throw this up here. PowerSchool had a Schoology platform. They need to be able to scale and respond quickly and efficiently. So a lot of these great use cases even came out during the COVID-19 pandemic when people were having to now do a lot more stuff online. A lot of the schools were actually leveraging technologies. But they were able to remote learn and scale to handle 650% throughput using Amazon Aurora. Right? You think about that and you think about, okay, any infrastructure that you guys have set up today, is it set up for 6 times or 7 times the amount of throughput? And how much did that cost you? And if you could run that at only the bare bones for most of the days, night times, depending on where this platform is being supported, you're going to save a lot of costs and operational costs in managing that. So let's get to step 2. Step 2 is sort of what we call sort of the next low-hanging fruit. So you've got these relational databases, you fine-tune them, you've moved them into the cloud. Now the question is, are there ways to enhance the platform? I've seen lots of customers, and this is an advice I'll give, start adding maybe more and more databases. When they realize if they just take a little time, they'll find out that the access pattern, that people are hitting the same amount of data over and over again. And instead of boosting up the size of the database or boosting up the memory, let's just actually use a caching platform to take off that repetitive operations, offload the session state or caching, and run it through a caching platform. So it's going to help you increase the performance. If you've got applications that have frequent counters, like rankings, or you need sub-millisecond data access, using a caching platform is going to be the key. So if you take a look at the AWS in-memory managed solutions, we really go from what we call non-stable to the stable side of the house with Elasticache, all the way up to MemoriDB, which was just released. In reality, this just gives you a stable platform to, if you don't really care if the cache goes down and you have to refresh it, if there's an outage or you restart the application, you can leverage Elasticache. MemoriDB was really created for applications that had maybe small subsets of data. They didn't want to populate it with a secondary data store in the back end and then cache it in. You can just store it in MemoriDB, and so it's going to remain durable even if you actually bring the database down. And just digging into MemoriDB, this is one of our newer services into the offering. So it offers the lowest query latency of any database by AWS. And so you've got MultiAZ data durability as well with Redis capability. And we use our distributed transaction log spanning multiple AZs to support that as well. So you'll see this quite a bit in most of our database technologies, being able to support across multi-AZs for the failover, failback, and durability for the platform, as well as being secure as all of our database platforms are as well. So step 3 out of 4 is now taking a look at the non-relational query patterns. So you can see as we're building our chart here on the right side, if you haven't noticed, we've gone from our relational to caching to now some of our key right tools for the right jobs types of patterns. So you'll see we highlight these with DynamoDB, DocumentDB key spaces, and these are really meant to be for supporting some of those microservices and those access patterns that drive them. And if we dig into those 3, DynamoDB is probably one of our, I'll call it, most used non-relational databases. It provides that performance to scale, delivers consistent sub or single-digit millisecond latency, handles millions of requests per second, you don't have any servers to manage. You pretty much, it's maintenance free, it's auto scaling. We get up to 5 nines SLAs, as well as being ASIC compliant, provide just as much security as we do with all of our other platforms, and some of our global tables. So being able to build global applications if your reach is far-fetching. And it's key for serverless and event-driven architectures, resilient services, or high throughput workloads. So if anybody's used, the best, when I talk to my friends who think I'm sure all of you are like I am because they hear you're at Amazon or you do IT and they ask you for desktop support. I try to relate it as one of the key uses I find for DynamoDB is all the online movie viewing solutions. So a lot of the organizations that actually stream data, every time you log in and log out, you want to go back in, you don't have to start beginning of the movie and get exactly where you get to. They're like, yeah, that's great. I log out and I log back in and I can start watching, Doctor Strange all over again. DynamoDB is keeping track of every point of where you're at in that movie. So when you log out and you come back in, it knows exactly where you're at. So there's a lot of high-ranking counters. If you write any of those, I try and give all these things without giving the exact names of the vendors. But if you ride some sports equipment and you're up on that leaderboard trying to track where you are, maybe you're riding a bike, you might be up there as well. So Zoom is a good example during COVID-19, keeping track of the global increase in the amount of throughput they had. DynamoDB was one of the key solutions in supporting their backend. So you can see the quote from their engineering managers using DynamoDB global tables with their on-demand mode allowed them to scale nearly infinitely with no performance issues. So when you think about that scale, I just like that quote because it allows them to scale, and they never found the top part of that scale. We were able to cover anything that they needed to at the time, which is in and of itself a pretty awesome quote. So DocumentDB as well allows us to help support a lot of those document-based applications. So DocumentDB is a MongoDB compatible database. Just like the other platforms, you can scale in minutes. We do auto scaling on the platforms. You can support up to 64 terabytes. Has built-in high availability, backups enabled by default, as well as monitoring and alerting. And this is really good for DocumentDB. Is good for content management, big data, and user or product profiles as well. And Keyspaces is our fully managed Apache Cassandra compatible database service. So you can take it with existing Apache Cassandra applications, new applications. Once again, handles millions of requests per second, performance at any scale. It is a serverless solution as well. So once again, fully managed, you pay it as you use it. And then last but not least, point-in-time recovery, fully provides encryption and identity integration as well. So really key for those schema validations, multiple independent sorts. And if you've got rows up to 1 megabits in size, it's going to allow you to scale from that side of the house. So just to wrap here in the last few minutes, step 4 is the specialized data interaction. So we talked about all the databases. Now we talk about some of our key, what I think are some of our pretty cool databases with Neptune, Timestream, qldb. This helps support like social graphs, recommendation engines, and also gives you the agility, scalability, performance of a lot of those purpose-built databases you may be doing on-premise right now. So if we dig into a couple of these, Neptune is our graphing database, supports property graph and W3C RDF graph models. It does query billions of relationships with millisecond latency, as well as being redundant and reliable. So Neptune's key for social networking, recommendations, fraud detection, life science. So think about, I always use the example of Neptune. If you go to Amazon.com and you want to look something up or you buy something, it's going to see, hey, this person, if they buy a broom, usually maybe likes to buy a Swiffer as well. So it looks for those relationships in anything you're doing out there in the environment. So I like this example with Marinus Analytics. It's a cool feature of what you can do with Neptune and helping something that's pretty important today. So Marinus Analytics had a database that was identifying trafficking victims. So before using Neptune and a relational database, it was very hard to go from 1 degree or deeper than a 1 degree of separation. So with Neptune, because of the way Neptune creates relationships and not necessarily connections between specific data points, it's tracking the relationships. They were able to go from 1 degree of separation to 2.5, which actually allowed them to collect and organize 350,000 data points daily, which reduced their query time over a relational database by half, despite having more times data. So just think about that, especially when you think about what's going on in the world, what kind of cool things you can do with this technology. If someone was missing, or a great example of this, it actually had a family member who actually tracked data for a police unit, and they would have to track all the different people that had connections, and be able to have this automatically done saves them a lot of the legwork and actually gets you to finding someone that could be in trouble faster. And Timestream, which is actually pretty cool with the time series database. What I love about Timestream, and I won't read this slide like I have some of the others, it's really meant to be to collect, store, and process data by time at any scale. So what's cool about this is, I think one of the greatest use of Timestream is the Internet of Things, right? Any of the IoT devices that are bringing data in, streaming them by the seconds, sub-milliseconds, and then you need to compare time series data with another time series data. You could use relational databases and use time as some sort of primary key, but to be able to draw the relationships through millions of rows needs a more highly performant database. So it's built in with our ML and analytics data collectors. A great example was, I like to give this one, an engine company. Every time an engine went up, they were collecting statistics on whether the vibration rate, the motor rate, anything that changed over time between that one engine was something that they would flag, or between all their engines in the fleet. So you can think about that. If a plane goes up hundreds of times, times hundreds of planes, that's a lot of data that you're going to be collecting on. And Timestream is a key platform for that side of the house. And last but not least is our qldb. It's our fully managed ledger database. Really provides immutable journal, and it tracks history of all the changes. So all the changes are cryptographically chained and verifiable. It is serverless and easy to use. So if any of those looking for some sort of blockchain or immutable tracking of your data, qldb is the platform. And so the last customer example I'll give out is FINRA. FINRA in the US is the Financial Industry Regulatory Authority. And what I like about this example, it just shows you how they took their environment. And when we say people are sometimes all in on AWS, they're finding the ways that they can leverage their platform. So they've taken their market data search, put it in DynamoDB, using caching with Elastic Cache. They use DocumentDB, Neptune for fraud detection, as I mentioned earlier, as well as using relational databases for their primary transactional database. So as I wrap up here with my last minute, now that you've done the modernization, the next step is unification and innovation. So you now have all the data that you're managing on the outside, have your data lakes, have your machine learning. Now you can take iterations. Now that you've got your data modernized, you can continually innovate, you continually continue to exceed on what you've now created in your platform. And so to sum it all up, on the 4 steps we talked about today, you have your relational workloads to manage your databases, implement caching and offload a lot of your in-memory workloads to pick off that low-hanging fruit and enable the performance. Take a look at your non-relational query patterns that you could leverage, and take a look at any specialized data sets that you could support out there. Saying that, you can continue your journey as well. If you've been in other classes, you've seen this. Definitely use Skill Builder to help build your database skills, as well as AWS certifications. If you have any questions, I'll stick around afterwards. And we definitely would appreciate if you guys complete the survey on this. Any feedback, good or bad, is always good. And appreciate the time, and appreciate you guys sticking with me. So thanks for the time.